Well, hi, good morning, and thank you so much for joining me in my shop. Today is March 22nd. Oh my gosh, the spring has come. No, winter has butted spring out here, and I think the city of Toronto is looking at 15 centimeters of snow later today, and it's the high today here is like -4 or something like that. Oh my gosh, winter has returned here. So, but as a Canadian, I can't complain too much, can I? So what we've done so far with this radio is simply replace the power supply filter capacitor, and that removed the hum, the overwhelming hum that was in the radio. And after that, I gave it a test. Its performance on its own was really bad. It couldn't pick up a station. But if I how can I say, if I provided the opportunity for the radio to receive a strong signal, very strong signal, then the radio worked. So everything's kind of okay in the radio, but weak. So I think I'd like to do this in some interesting approach, do the restoration, an interesting approach. So I think what might be interesting is trying to find out specifically, why is this radio so quiet? Now, one very possible reason is a weak tube. In fact, that's really the first thing we should be suspicious about, really. These are fairly easy things to test. You're not disturbing the radio that much to do it, so you're not going to introduce errors and problems and stuff like that. So it's a low risk thing to do. There's 1, 2, 3, 4, 5 tubes. One of these is a rectifier tube. I think that's the one we should start with. And which one is it? I can't tell. These are all so dirty. I can't see. These tubes all have their names on the top here. So these are not your ordinary, everyday, run-of-the-mill tubes. Is there such a thing? I don't think tubes are running the mill anymore. So to pull these tubes out, because these are locked in place, you first come down here for a better look. You look at the socket for the tube, the socket that's mounted in the chassis. And you can see a rivet. There's a rivet there. There's a rivet there. The rivets here, here. So you look for those rivets. Well, then you take the tube and tip it towards the rivet. There'll be 2 rivets. You can tip it either way. Obviously this one can only go this way, and you tip it towards the rivet. It's supposed to pop out. Oh my gosh, well, you know what? That may not have been a good idea. Can you see what's in there? I ended up with part of the tube socket in there. I've never ever had a tube socket shatter like that. Look at this. Oh my gosh, it's shattered in pieces. Well, that's really upsetting. Really total surprise. Probably just leave it the way it is and continue to use it. But all this kind of light-colored brown plastic is very fragile. It's cracked. And my technique of tipping this, I don't think it helped at all. So that's really about the 3rd time I've removed one of these Loctile tubes. Now look at the base of it. It has a metal prong. I mean, most tubes have a plastic prong coming out, and can you see it's kind of indented right at the end here? That's to snap into something. Snap in, it won't fall out. The pins are smaller. Then the 2 of them are, there's no pins here. They didn't break off, did they? No, they couldn't have broken off. No. So back before I learned this technique, which now appears to perhaps cause this damage, this is what I would do. I would stick a screwdriver under it and do that. Oh, look at this one. This one's also cracking up. Okay, let's not pull all these out or I'll end up losing track of what tube is where. So this is the output tube. 50A5, that's what we saw on the schematic. When renewing, always request a Philco tube. yeah, this was the money maker for these guys. Okay, we're going to start tube testing. We're going to use a dynamic tube tester, this one here. But before we get going, I'm going to stop and treat myself to some coffee. Then we'll start testing these tubes. Okay, here we go. There's the tube tester I'm going to be using, and you can see I have a close-up camera on the actual dial here. This is very hard to get this on video so you can read everything. That's so it's just not going to happen. So 50A5 right there. Here. So I've dialed up on the sheet here 50A5, which you cannot see. And we're going to go across and do all the settings for it. So the first one is the filament voltage 47 on here. It's really 50 volts, but on this tube tester you set this to 47 volts. Signal level 8, which is a high signal level. The bias 21, and then this is set to H for high. So, and then we set these switches here. Oh, 1 second. I took the time to set up a microphone here, and then I forgot about it. Let me just check something here. Yeah, let's try that. Okay, that might sound a little better. Okay. Alright, I was going across here, getting ready to set the numbers. 50A5, so 73400. 73400 and 5160. 5160. Let me just double check those. So 50A5, 73400, 73400, and 5160. 5160. Okay. We set the meter sensitivity to 47, like so, and we select the plate switch, and we put it on C. This particular tube in this tester must come up to 1040 on the dial here. 1040 is just above where my finger is there. Actually, you should be able to read it. 1040. Yeah, you can read it. I don't usually put the inset video when I'm doing this, but I did this time. Okay, we got to figure out what socket this goes in. This must go in. Let's go in this one. Okay, let me just re-aim a little bit here. Maybe I'll stick it over this way. Go like that. There's not much to see here. I mean, I'm just going to pop the tube in. There is a key. Whoa! Whoa! Boy, that was almost the end of that. Wow, that could have been pretty exciting. Okay, so you can see the tube is warming up. Now, the first test we want to do on the tube is called a short test. And this is to find out if there's any elements of the tube have come into contact and are shorted out. Now, we've already had this operating in a radio, so I don't think that's too likely. So I'm going to operate this switch. There's 5 settings. Each one is testing a different combination of the elements in the tube. And you're watching the meter. The meter will pop up a little wee bit. If it comes up scale, we're in trouble. There we go. Didn't even pop up really much at all. Ooh, what was that? Don't think that's anything. Okay, we're all set. So to test this, we're going to throw this switch here, which says GM test, which is transconductance test. And it's supposed to come up about 1040. Let's see, if that's 1,000, that's 1,500, 1040, just above here. Here we go. Oh, she's a big winner. Nothing wrong with this tube. Okay, that's it. Output tube is good. That's very good because these tubes are becoming rare. Yeah, I'm not gonna put that tube back in without doing a little bit of cleaning of the socket. So this is the next tube we're going to do. 35Y4. So this is the rectifier tube. Oops. Nope, shouldn't have done that. Okay, rectifier tube. What did I say? It was 35Y4. A tube I've never seen before. So we'll dial up 35 here. 35 Y4. Here we are. Y4? I don't know. 35. So we set that to 35. It's a rectifier tube, so the signal level has no impact. Bias has no impact. The settings here are 73000 and 0160. 0160. 23 on here. And very importantly, plate is on E. So in this case, now, if you look at the dial, if I can make my camera a little better here. If you look at the dial, you'll see right in here it says rectifiers OK. Over here it says diodes OK. And the idea is you just have to get into this area here, anywhere into this area. You're not reading the top scale anymore. It's just down here for rectifiers. That's what we're going to test. Okay, I'm going to double check the numbers here. 35Y4, 35, 7300, 73000, 0160, 0160, 23, E. We're good. Okay, we'll pop this in. Now, if you're sharp-eyed and I didn't put my arm in front of it, you might have seen the pilot light flicker a bit. When you put a cold tube in, it draws a lot of current initially, enough to dull the pilot light. That in itself is a test. You can look for that. Whereas all these tubes, the heaters must be operating, they're all in series in the radio. And if you notice, this tube is a 35, the other tube was a 50, and then we got two 14s and a 7. Well, I think the 14s are actually 12 volt tubes. I think if you add all those numbers up, I'm not going to do it right now, it'll come very close to the line voltage, 115 volts. Okay, we're going to look for a short. There we go. Any shorts in this tube? No. Okay, it's safe to test. Pushing the rectifier and diode button and watching it come up into this area. It's a winner. It's a winner. So this one I can put back in. I'm going to take the next tube out, whatever it is. Okay, the socket has survived. This guy is a probably 14A7. I think is what that says. Magnifier, please. Where'd you go? The magnifier has wandered away. Huh. Shoot. Okay. Different magnifier. I'm not going to be able to see it with this. No. I've lost my little magnifier, which I use multiple times during the day. Okay, I want to be absolutely sure. I don't want to make mistakes. I think it's a 14A7. So I'm going to stop for a minute, probably drink some coffee too, and just double check the schematic. Make sure I got the right tube number. Okay, here we go. So I've got this set for the 14A7. 14A7, let's double check. 13 for the heater volts, at least that's the number over here. I think the voltage is actually 12 volts. Signal level 2, bias set to 29 low. The numbers are 73421, 73421, 5160, 5160, 44 C. Okay, we're ready to go. Whoa! How many times am I going to do that? Yikes. That's it. Okay, don't push too hard. Oh, boy, I tell you. That's why I don't like doing unnecessary things to other people's radios, because at any moment I could like drop it on the floor or something. You just don't know what bad thing could be happening. Unintended thing. Okay, looking for shorts now. There we go. None. If a short showed up, if this meter had come up, then it would be unwise to continue the test on this tube and push the test button down here. But we are going to push it now. So a 14A7, the reject point is 1350. So, 1350 is somewhere right around here. That's the reject point. That's the point at which the technician can sell a new vacuum tube to his radio customer. But generally, these tubes keep working quite a bit lower. You're not getting the performance you might possibly want. So, not to throw away a tube that simply doesn't meet the number that's written on this tube tester. But that would be the indication back in the day. Here we go. Oh, way, way, way over. Fantastic. The tubes in this radio, I'm getting the impression that this radio did not get used very much. That's the impression I'm getting. In the tube. I'm just over here getting out the next tube. The next tube is, there we are. Right. So I don't want to just take a cloth and wipe this off. I might wipe the numbers right off too. Let me take a peek at the schematic. This is the first tube in the radio. So that would make it a 7A8. Can I see any of that? I never found my magnifier. That's because I really didn't go looking for it. Okay, I'm going to wash this up just a bit. Hang on there. Okay, let's see what we got now. Again, I don't want to wipe over it. There we are, 7A8. Okay, positive proof. I'm going to set this guy up here. 7. 7's over on this side. 7A8. There it is. 7A8. So 6.3. So, most tubes start with the number 6 or the number 12. And that represents the voltage of the heater. This tube has a number 7 on it, but its heater voltage is not 7 volts. It's also 6 volts. These tubes were kind of a, I don't want to say anomaly. These tubes were popular for a short period. They have this locking stem, which makes them attractive because they lock into the radio. I guess the tube makers didn't want to have these tubes mix up with the other tubes just by number. They wanted to identify them separately. So somebody said, well, instead of calling them 6, let's call them 7. We'll all know they're 6-volt tubes, but we'll just call them 7, and we'll all know that these 7s are the Locktal. Double that for 14 instead of 12. That's how they get this number 7, when in fact 6 is the voltage. And the set wrong. 6.3. Are we ready? I hesitated there because I'm thinking, did I have the voltage wrong for the last? No, the last tube was set to 13 here for 12 volts. That just adds the confusion too, because the number, for some reason, the voltage numbers here don't match the actual voltage. So for instance, for a 50 volt tube, you set this to 47. The actual voltage that's being impressed upon the heater, I don't really know. I would think it should be 50. I don't know why these numbers are the way they are. So for instance, a 12 volt tube gets a setting of 13 here. Okay, let's go. Let's go. Anybody, any leaks here? No. Am I retesting the same tube again? So it was a 7A8. $13. Yeah, this is the same tube. Oh, I don't. What am I doing? What am I doing? See what happens when I've lost my mind totally here. A total mind loss. 7A8. That's a total mind loss. Does that happen to you? My wife and I are complaining about it all the time. That I think it's because the world of information that comes at us is fast and changes topic like this, and our brains have accommodated that. So now our brains are, they continue doing this even when we really don't want them to. Yeah, this is a 7A8. I can't remember what I did. Do it again. Do it again. 7A8, because we got a 0 on this. 6.3. 2. Oh, I did not set this up. Oh my gosh, what happened to me? I get too many thoughts in my head. I think that's what it is. 8. L. Yeah. 73454. Well, I know why this wouldn't. 4, 5. With the wrong settings, you're not going to get a good reading. 5160. 51. Probably stand a chance of damaging the tube tester. Having the wrong settings here with the tube in place. Okay, I think I got it right now. Let's double check, because I'm talking and thinking and just not thinking, and it's crazy. 73454. 73454. 5160. Okay, I think I know what I'm doing now. Now you might think vacuum tubes, old simple devices, not like the complex modern transistor devices, but it's really the other way around. The transistors are really quite simple in many respects as compared to what goes on inside a vacuum tube. Okay, here we go. No leaks. I'm going to give it a GM test, and the expectation is 7A8. Whole tube test 975, so just under the 1,000. We buy a new tube. Right up there, another winner. So these tubes are all testing great. So we're losing our explanation for why the radio's output is quiet. I only have one more tube here to test, and if that guy's good, they got no way of explaining what's going on. I'm just going to pop the tube out here. Not using the technique that I showed you. Okay, so I can read this as a 14B6 is what I see there, and that matches the schematic. What is the 14B6 doing in this radio? This is the detector tube. So this is a busy tube. So this is really two tubes in one. It has some diodes in it that it uses for detecting the radio signal, and it has an amplifier in it that it uses to boost the audio before sending it to the output tubes. It's actually, in the odd radio, this is 2 separate glass tubes, but most radios, the tube manufacturers figured out they could combine this into one tube and make everything cheaper. Okay, I'm not thinking very hard. 14B6, or I'm thinking too hard. 14B6. 14B. There it is, 14B6. 2 tests for this tube because it's 2 different tubes inside there. So voltage 13. Kind of whack the camera there. Signal level 1. Bias is set to 21 low. The numbers are 73500, 73500, 735. I was distracted there. Don't be distracted. Don't get distracted. 0160. 0160. You know, how do mistakes happen? For me, all kinds of ways. Okay, double checking now. 14B6. 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 Yeah. 13 on the heater, 1 on the signal, 21L on the bias, 73500. 73500. 0160, 0160, 40F. We're good. Here we go. So I'm hoping this tube's going to be bad. Why? Because that'll explain the low output on the radio. Well, let's find out. Now the other tubes all tested quite good, so really, you know, if I had to put money down, I'd say this tube will test good too. They're all traveling in the same ship together. There we go. Okay, this tube, 14B6, on this test should show 710. So it only has to get up to about here. There we go. Wow! I don't know, was this radio ever played? Now we're going to do the next test. I'm going to take it out of the socket while I make changes. So don't care about this, don't care about that, because there's a diode that's coming. 70003. 70003. P160. P160. 48. A. I got it right now. There we go. 13, nothing, 7003, 0003, 70003, 0160. No. P160, P160. Almost blew it there. 48, A. Okay, Mr. Diodes, how are you going to do? So for the diode test, there's a bit of a light problem here, so I'm going to hold my hand in the right spot. So here you can see the diode OK box down here, similar to the rectifiers over here, but this is how high that's good. Just has to get into this box, and she's good. Okay, I was trying to block the light here with a towel. Yes. And it's not going very well. Hey, there we go. Okay, so first of all, any shorts appearing in this setting? No. And we're pushing the rectifier diode. Here we go. Good. Okay, you know what? All of the tubes in this radio are in really good shape. Very good shape, in fact. So I don't think this radio got much mileage. That would be my guess. How you end up with so many tubes in such good shape. Okay. Well, if it's not the tubes, it's got to be something else. What else could it be? I'm going to go ask my coffee cup that question. I have not consulted my coffee cup yet. So there could be a number of things that are keeping this radio quiet. Everything from the alignment may be way off to the more likely a defective component, capacitor in particular, and a possibility of an incorrect voltage in the radio, and that would be because of a resistor has gone off or something of that sort has happened. So there's quite a few ways to go here if we want to I would like to know what the problem is with it, just because I enjoy that, not because it needs to be known. You could just go in and start changing the few capacitors that are in there, and likely, there's a good chance, bingo, the radio would come to life. But I'd just like to be a little more sure about what's happening, and at least convince myself I know a little more of what's going on. And now I will go and visit my coffee cup. Okay, what's next for this radio? So I think a little bit of testing is in order, and there's two approaches. They're kind of the flip of each other. One approach is feed in some signals, hear what comes out of the speaker, different signals at different places in the radio, and hear what comes out of the speaker, and make judgments based on that signal injection. The other way is to listen to the signals that are in the radio. Listen to them here, listen to them there, maybe listen to them progressively through the radio, and find out where suddenly the signal fails or weakens or is not what you would think it would be. So those two approaches, in a radio like this, I think the listening one is not a good idea, because there's a good chance the signal's not getting much of anywhere into the radio. I think it would be better to start feeding in signals close to the speaker, maybe starting with actually an audio signal, and then hear what comes out of the speaker, and then we can put in radio signals earlier and earlier in the radio and just keep listening and see if we can identify where the weakness occurs. It could be, it's kind of, the weakness is kind of spread through the radio. There's 2 or 3 or 4 capacitors all adding in or maybe subtracting away and making the radio weak, so there's no one thing that can be identified. But I bet you there is. So to do that, I think I'm going to tip the radio this way, like this, and that's very good. That's good. That's quite good. And what we'll do is I'm going to feed a signal into the volume control. The volume control sits in a very particular, most of these radios, 95% of them, the volume control sits in a very particular spot where the radio goes from manipulating radio frequency signals and begins manipulating, amplifying really is all it does, amplifying audio signals. So there's an RF part, a radio part, and then there's an audio part, the speaker part. And I'm doing this, it's something like that. The volume control sits right in the split between the RF and the audio part of the radio. So you can listen at this point to hear what's coming out of the radio without paying attention to the amplifier, or you can feed a signal in and hear what comes out of the speaker, and then you know about the condition of the audio amplifier. Let's do the signal in thing. You see this capacitor right here, and it's hooked up to the volume control. If you look, it's hooked to the center terminal of the volume control. So that's the output of the volume control on the center terminal. So the output from the volume control goes through this capacitor and onward into this tube. This is the tube that does more than one thing here, and it's going into the audio amplifier part of the tube. So you could have good audio here, nothing over here because the capacitor is bad. That's possible. And that's possible. Not much else to say about it. The entire radio signal at full volume is fed to the volume control on probably this white wire here. Probably this white one. And the other side of the volume control is usually grounded or tied back to B minus, or the, I don't know what the right word is, B minus, I guess. So the entire output of the radio is sitting on the volume control, the entire audio output, and then you're selecting how much of it you want to move on to the rest of the radio through this capacitor. So we listen here, we hear the entire radio. If we inject a signal here, we can find out if that signal will make it through the radio. Let's start with listening. If the audio is weak and the radio is good, then we'll pick up a strong audio signal here, but it won't be coming out of the speaker. Yeah, let's try that. That sounds like a good idea. So to do that, I'm going to use this signal tracer. All of my equipment, or virtually all of it, is vintage equipment from back in the day. So that's kind of neat. So this is a radio receiver here. It's used as a signal tracer. Here, tracing the signal with this great big honking thing here, and this is the ground connection, which we would either put on B minus or on the chassis, depending upon how we want to do it. This can also work as an audio amplifier. The switch down here switches it from a radio to just an audio amplifier. Right now it's set to audio amplifier. This control, and this control are all manipulating the volume. These are to cut down the input coming over here, and this is to increase the output at the speaker. There's a magic eye, a little hard to see, but there's a magic eye here, and you can do semi-quantitative measurements using this if you wish. So, going back to the radio now. Now, when I'm plugging these devices in on my bench, I'm not just plugging them into a regular outlet, and I'm not just plugging them into dim bulbs here. I also have a isolation transformer powering all this, powering this. Now that means there's no relationship between the 120 volts that arrives here and earth, or the power system ground, or anything like that. And this improves my safety here because I cannot get a shock to ground. And I'm not likely to because I'm well insulated, and I try to be careful. Now what do we do with a negative from a signal tracer? We can obviously clip it onto the chassis here, or we can clip it right onto the B minus, which would be the negative of the filter capacitors here. Probably in this case, probably better to go on B minus. If you go on the chassis, there's a chance there's going to be a hum that's going to show up, and you won't be able to deal with it very well. And this is too big a clip lead to have hanging out of a radio, so I'm going to use a little clip lead here. I'm going to pick off the negative. I'm going to clip it where it's good and secure. Clip leads have a way of wandering. I'm just going to clip it to the ground. If I were plugging this into a regular outlet, first of all, I would fill my pants. I'm not plugging this into a regular outlet. Look, it's not polarized. I really haven't examined 100% what's going on with the supply wiring. And I wouldn't do this. Not without getting out a voltmeter and doing some other tests. Because, you see, it's not polarized, right? So we can plug it in this way. You can plug it in that way. You might think it has no consequences. But in a 5-tube radio with no transformer, this can have very big consequences. But because I have an isolation transformer, most of those consequences are moot. Would that be the right word? Moot? Okay, we're going to be turning this guy on. I do not have an antenna connected. I should put, we want to hear something. I think we want to hear something. We're better off hearing something. So I'm going to, so this box up here is just connecting to an antenna cable that runs circuitously through my house and eventually goes outside to a tiny little antenna. There's no wires going out or anything. It's not a loop. So what do we do with the antenna? Well, the last time I used a loop stuffed in the cabinet, and that seemed to be just enough. So you don't make a direct connection. So all that's happening is my antenna outside is powering this loop with a tiny, tiny amount of power. But radios are built to work with tiny amounts of power. So I'm going to put this in here. And we don't want it moving around, or it's going to make our test questionable. Put it like that. We want it to stay put. Maybe I'll even improve the stay putness here. Not with this. You know what? I'm going to do it over here, because if it moves even a little bit, we'll just be raising questions too. So I'm going to clip it there. So that loop will not move relative to the antenna, which is inside the cabinet here. Now I'm going to practice. What am I doing? I want to touch the volume turned. Power's not on. So the volume's low right now. So I would want to do that, made me jump. Touch there. Must have been a little voltage sitting there or something. And then I'm going to turn it up just like this. And we're going to hear what comes out of the speaker behind me. At the same time, it will come out of the speaker here. It's going to be a little hard to work out. It'll be hard. We'll leave it at that. I think we're all set to go. That means that I should go drink some coffee now, I think. There's something else I had in mind. Well, it's not in mind anymore. It's gone away. Okay, here we go. Now, the idea of this test is, or the way this is going to work, is I'm going to tune in a station. We're going to hear it on the speaker of the radio. We'll probably have to have the volume turned up pretty much full, if I remember right. That would give us an idea of the strength at the speaker of a signal. I'll then turn down the volume so we don't hear this speaker anymore, and I will then apply the signal tracer to the input side of the volume control. That's actually a little tricky here. It's actually too tricky. I have to move this. Like that. Only the other end of the wire. Yeah, actually I can get it on the other end of the white wire. It's a white wire going to the terminal back there, and it comes over to the center terminal here. So by touching this, you'll get the input, the output of the radio, or the input to the audio circuit. So hear what it sounds like there, hear what it sounds like over here, judge the relative volumes. Then you know radio putting out a strong signal, audio amplifier weak, or radio not putting out a strong signal, amplifier probably fine. That's kind of what we're trying to do. So we're sort of picking the center of the radio and taking a look kind of in both directions, what's going on, and kind of like that. Maybe I'm stretching it a bit there. Okay, so we're ready to turn this guy on. Yes, we are. Here we go, dim bulbs. Away she goes. Now we need to turn this up. It is up. And then we're going to need to tune in the station. Wait a bit. A little bit of crackling there. Okay, find me a radio station. Oh, we're going to have a full voltage here. Full voltage today is 113 volts. Okay, now we're going to tune. Give me a station. Any station. Way down here. Oh, nothing. Okay, so did I really turn it up? Maybe I didn't turn it up. I did not turn it up. Station. too bad about that interference. I can't do anything about it, I'm afraid. So, you can hear the radio station playing. Right? If in fact the signal is the volume it's at now because I have the volume turned full. No, I don't. I do not. What's the problem here? Where's the problem? Problem is if I take that loop out of there and just let the radio try to do this on its own, it's very, very weak. You know, I'm starting to think it's more an alignment problem than anything. Let's carry on with the test though. So I'm going to turn this right down. All we're going to hear now is what's coming out of the signal tracer. I got my hand on the volume so we don't get blasted. And going on here. Okay, I'm going to turn it up. So a little hard to judge now what that actually means. Based on the fact that turning this volume up, the radio gets quite loud. It's just full of noise because it's having a hard time picking up signals. But that again sounds like alignment issues. Let's skip to checking the accuracy of the alignment of this radio. That sounds like there's a couple things we can do to see, especially if the IF is aligned properly. Let's take a peek at the schematic here. So here's the volume control right here, and this is the signal coming out of the radio and the audio signal, and here it is on the volume control, and then some portion of it is fed on into this multiple tube here. This is one part, this is the other part of the same tube, just showing on the other page basically, I guess, and then on its way out. Getting lots of volume coming out of here, noise and stuff like that, but not getting much program material coming out. So and a little bit of static there you just heard. Now let's go look at the earlier part of the radio here. So what a radio like this does is it receives the signal here. You know, let's say it's I don't know what I'm tuned to here, but let's say it's 680 kilohertz. There's a station there in Toronto. It puts it through this tube, and when it does, it changes it from the 680 to a new frequency of 455. That's what we need to find out. Is it 455? Somewhere in here there's going to be a note about this transformer. So this is tuned to 455. And front of the radio tuned to 680, but inside it's fixed tuned to 455 kilohertz. I'm guessing the 455. Somewhere they're going to tell us. Let's go down here. There it is there. Big bold print. IF equals 455. That's the most common frequency for the IF, but not, it doesn't have to be that frequency. So this is tuned to 455, and unfortunately to see the other page I got to go down here. And there's another transformer over here. There's two of them. See, each one of these coils has a slug that can be tuned or moved up and down in this coil, and this will cause the coil to tune against the capacitor that's sitting here. You put a capacitor and a coil together in parallel, you have a tuned circuit. So the idea of this is you fix tune these things to a particular frequency, 455 kilohertz in the case of this radio and most, and then so you can, because this doesn't have to tune a range of frequencies, you can design this to be very high performance, put it that way. If you had to tune all this to 680, like all these stages had to be tuned to 680, oh, that's a tough one. But all you got to do is tune this guy around 680, convert through this tube to 455, and away it goes. Of course, the 680 is converted to 455, but another station, 740, would be converted to 495 or something like that. 495 won't go through, so you won't hear it. You'll only hear frequencies which have been shifted to the IF frequency. In fact, if we were in England, and maybe you're in England, this is called a frequency shifter. For some people would call it a frequency shifter. That's actually a better description than a converter or a mixer. A mixer's not a bad description either. I won't go into how they do it, but they do it. They manage to shift the frequency to the IF. Now, what if the IF isn't tuned properly? What if this one is 455, and that's great, but the next one is mistuned to 490? Maybe this one coil, tuned to 490 somehow. Well, we're going to have a hard time getting the signal through here because it's not tuned to the 455. So 3 of the 4 coils here are happy, one of them would not be. And that's enough to knock the signal way down. So we want to test this. So how do we do this? So we feed a signal through this, not the 680 type radio signal, but an actual IF signal. I got a signal generator here. I can set it to 455 and I can feed the signal in. Well, we could feed it right in this antenna. We can feed it right in. It's going to go right on the grid of this tube, and it's going to go right through this tube, and it's going to go through the IF. Now, if everything's tuned right, then when I send a 455 through, we get a peak coming out of a peak volume coming out of the speaker. I'll do this with a tone, so you hear a tone coming out of the speaker, and then I can vary the frequency up and down from the tuned frequency of 455. I can move it up and down, and we can listen, or I'll hook up a meter and we can see what frequency generates the loudest sound out of the radio. If everything is good, that frequency will be 455. If things aren't, it won't be. So we can do that test. So that's what we're going to do. Check the IF to see if it truly is tuned to 455 kilohertz. Just because many of you, perhaps you who are watching this, are also radio people and experimenting around. So this is going to the B minus, and this is going to the power system ground. The radio is not grounded, but when I clip this on here, there will be a proper power system type ground on the radio. Can you hear the signal? Can you hear the guy talking? Not if I do that. Okay, so this is a case of where I'm trying to demonstrate something, but the demonstration just doesn't do it the trick at all. You were supposed to hear his voice disappear. I think what it's doing is increasing the noise level. I think that's all that's happening. Okay, there you are. Totally failed experiment. So I'm just getting my signal generator warmed up here. You can see it's at 1500. Let's put it at 455. Now, how am I going to feed the signal in? First of all, the least impactive way. Let me get this out of here. I don't like this being here. Okay. So I'm going to use the same loop. Wow, see, I disconnected that loop. So that noise signal is on my antenna system. Something terrible. And also, the radio itself is kind of deaf, so it can't hear this noise. I'm sure it's here in the shop. Don't say you're sure. Telling people what you think. What do you actually know? So let's try... Oop, where'd it go? Battery check. Okay, so oh, there we go. Oh my gosh, yeah, my battery's too low on this guy. Yeah, okay, I think it's off. But you heard the noise there briefly anyway, the ticking and that, so I can't even, what am I doing here? Okay, we're going to hook up the loop that's laying in here to the signal generator. You can hear it already. Let's turn this up. Now, it's tuned to a station, so we can't have that. So I'm going to tune it off. There we go. If we have a station, you're going to hear a whine. a heterodyne line. Volume is full now. Are we hearing the tone from the signal generator? My signal generator produces two tones, 400 Hertz and 1000. Okay, the 400 Hertz is not being reproduced in the speaker well enough to hear it, but the 1000 is there. So I'm feeding over, not that it matters, a moderate signal into this loop, but it really doesn't matter. What we want to do now is increase this a little bit, I think. That's better. And we're going to check calibration. Calibration's way off. There's no reason to calibrate this, but I like to. Okay, we hear the tone. Now I'm going to, and you can read the frequency, 454. You got to add 1 to this, 455 to get it, because it's a little low on my vintage equipment. I'm now going to tune down. We just want to listen. Does this get louder or quieter? Quieter. And disappears. Now we'll come back up. Now we'll go up. Not bad. That's not bad. It's very close. I'm going to go a little off hunting here. Nothing going on. Most radio IFs are pretty close unless somebody's monkeyed with them. So, this stuff gets done in the factory and it doesn't drift all that much in most radios unless something's been done to them. So, I think from this test we can say the IF is well tuned well enough that it cannot explain poor signal response. Another area is the RF tuning, but in a radio like this, I just don't think you're going to get a big boost out of it. I just don't think that's going to happen. So what we can sort of softly conclude now is it's one of these guys that's doing it. One of these guys is responsible. So we can, and this one, I've got to keep telling myself, don't touch that one. Leave that one alone. So who would quiet down this radio? Quiet down the reception. Not the audio side, but the RF side. Let's take a look in the schematic, and I'm not sure of the answer. Let's take a look in the schematic here. And again, you could just get in there and change those capacitors and be done with it. We'll go this way. But I like the fooling around part. So if we assume it's something happening in the front end here, we are looking for some capacitors that are out here. Okay, that's a picofarad. This is a tiny capacitor. This is a tiny capacitor, and of the sort that you don't normally have trouble with. Okay, there's nothing here. These capacitors are inside of the can, the IF cans. We can't get at them. Here's one that's interesting. At 0.05, and you see it's connected to the screen terminal. Probably same thing on this tube, of course. Yeah, two screens in this tube. 40 volts supposedly on there. And this capacitor's job is to quiet this line down. That's not a very big capacitor there. Yeah, that's not very big. 0.05. Often there's like a 0.1 or something in this position, something larger. Let's look at the other part of the schematic. So this is the same one, isn't it? 304? Then I was at 304. 303. It's not the same one. Oh, no. Up here. 302. Yeah, and this is a different one down here. This guy. And he's on the... where is he? So this is the output from the diodes here. A little odd how they've done this. Okay, it doesn't matter. This is the start. I don't want to say it that way. So it looks like what they're doing here, I know what they're doing here. So they're using this diode, there's two diodes in here. They're using this one diode for the detector, part of it to detect the audio. It's going over to the volume control, and you can see they've heavied up, the draftsman heavied up the lines here to show the signal path. This other one is being used to generate the AVC voltage, automatic volume control voltage, and that is being sent off to the grids at the front of the radio. You change the bias of the grids on the first two tubes, you change their amplification factor. So you can, in effect, change the voltage here and change the volume of the radio way at the front. So there's a good reason for that. And this capacitor, and we can call this the AVC capacitor. So the two capacitors I've looked at, I wouldn't think either one of them can do any monkey business. Look at all these capacitors here. These are all inside the metal can. See the dotted line? So they're inaccessible unless you take this can off and dig down for them. So, but no reason to do that. These are tiny capacitors. They are almost certainly mica capacitors, which are highly reliable. They're not perfect, but they're highly reliable. Whereas these paper ones I'm looking for, they're not very good. Okay, let's try something different. Since this isn't going so well so far, let's do something we need to do anyway, and that's, maybe I'll end the day by doing this. Let's check this capacitor. So this one here is very important in the radio. This is a blocking capacitor, and it's trying to block the plate voltage from this tube, 45 volts, from getting onto the grid of this tube. This is the output tube. So you have to supply some high voltage, this isn't very high by the way, on the plate to make the tube work, but then that high voltage is in the way when you're going to the next tube. You've got to stop it from getting there. So you put a capacitor here, won't pass DC, and you put a resistor here down to the B minus, and that'll pull the keep the grid right close to 0 volts to the chassis. But if this capacitor is leaky, the pressure of 45 volts here will push some charge through, will get over here, and then this resistor is 500,000 ohms. It'll only bleed the charge off slowly. If it bleeds it off slower than it's coming in, then you'll build up a voltage here, and the voltage will build up to the point where it's pressuring this resistor enough that the charge leaving is the same as the charge coming in. That circuit will settle down at some positive voltage. We don't want positive voltage here. We want negative voltage. But in this tube, they've done something interesting. Now, not interesting. This is a very common way of doing this. You need this grid to be negative a few volts with respect to the cathode. This is the cathode right down here. The grid is always a little negative to the cathode. But sometimes it's tricky to make a grid go negative in a radio like this. It's difficult. There's no negative voltages easily available. Okay, and I'll counter that right away by saying this diode generates a negative voltage, which is used on the grids of these tubes up here. How do they get a negative voltage on this grid? They don't. Instead, they make the cathode go positive. The cathode goes positive a little bit, 5, 10, 15 volts. Relative to the grid becomes negative. I'm sorry, let me rephrase that. The grid then appears negative relative to the cathode. And this is called cathode biasing. It's very, very common. And this is the cathode bias resistor. The current flow through the tube from cathode to plate. The current generates a voltage in this resistor. And the voltage is something like 5, 10, 15 volts. Depends on the tube, what you want. And there you are. As long as the grid stays then at 0 and the cathode stays at whatever it is, 10 volts, the tube is properly biased. Well, what happens if some positive charge leaks through here? Positive charge leaks through here. That's really, I'm playing around with words here. It's all about electrons. But anyway, then this would be pushed somewhat positive. So maybe you get 10 volts here, and maybe this is pushed positive 5 volts. And then the net bias would be minus 5 volts. Well, you really need minus 10 volts. And what happens if it goes to minus 5 volts? Well, if you under-bias the grid, more current flows through the tube. You don't hear it in the speaker because it's just a steady current flowing through there. There's no transformer action to hear it. And that's the key. You can't hear this. So positive voltage coming over, bias failing to be as negative as it should be. More quiescent current or through current or whatever you want to call it in the tube. Now what's that doing? Wearing out the cathode prematurely. The cathode is made of a material that, if you're not careful, can wear it out exceptionally fast, or just wearing it out unnecessarily fast. So we need to know these things about this. This is what we need to know. We need to know if there's a positive voltage here to ground, or to B minus. We need to know what the voltage drop is across this resistor. And this capacitor, which I haven't mentioned, is not what I was going to say. It's a good thing I didn't mention it. Just to clarify what I was thinking there, for those of you who understand this stuff. I thought this was a bypass capacitor, but I see, no, of course not. It would have to be up here, going down there. There's no bypass capacitor. Fine. Okay, let's check that. Voltage, is this radio in trouble? And it's operating here beside me, so let's just pop over there and take a look. There, we popped over. Okay, need a voltmeter. Let me use where's my green monster? Here it is. Let's use the green monster here. I like the indicating meter here. So we're going to be looking for a voltage, a fairly small voltage. We're going to look for, I'll set this to 30 volts. Voltage is relative to the B minus. I've got to clip this back on that B minus point with the radio operating. No, I'm not going to do that. Radio off. You see, if I am attaching this clip, and while I'm doing it, I make a big spark, I could jump. I could jump and pull this radio right off my bench. Okay, I don't know. So it's not about getting shocks and stuff like that necessarily. Okay, we're going to put this on here. Interesting, it makes noise, huh? Don't know why. This meter itself actually generates noise. This is full of transistors, this guy. This is a transistorized vacuum tube meter. After vacuum tubes came this. And then finally came the meter that all of us use these days. And it's this kind of guy here. This is a high input impedance meter. Okay, so we want to read the voltage. I have to put the schematic up on my computer here because I'm losing it. Right. We need to get on pin number 6 and pin number 7 of the output tube. Output tube's right here. Pin number 6 and pin number 7. Okay. I think that's 1, 2, 3, 4, 5. This is pin number 6. I didn't see anything go. I went backwards. Yeah. Okay. Well, the meter was set wrong. The meter's now set right. Ooh. Well, that was an exciting moment. So it's this part right here that just cracked open and blew. Oh, There's a terrible smoke in here. I've got to get out of here. I got to make a run for it. I don't want to breathe this stuff, so I'm making a run for it here. Well, that was pretty exciting. A very strange smell. It smelled very sweet, fruity sort of smell came from it. Not what you would imagine. So we're gonna look into this tomorrow. I'm done for today. The other things I did came out okay. It's just this part blew up. And it's probably just a capacitor, and we'll look into it tomorrow. So thanks a lot for watching to this point, and hopefully I won't burn my house down. My wife was a little upset when I told her what happened. Gonna burn our house down. No, I'm not gonna burn the house down. Thanks a lot for watching. We'll see you. Bye bye.